So Nathan, how'd you get into astronomy?
Well, actually, I started out as an undergrad. I was a music major,
Wow.
but I was interested in, I had liked physics in high school, so I took an astronomy class as a freshman, and it was pretty interesting. And then when we got to the part about stars, I actually decided that I wanted to major in it because it seemed very interesting. So I double majored, and then toward the end of my undergrad career, I was still planning to go into music, but I became more and more interested in astronomy, and I started doing some research projects. And after that, I decided I wanted to go to grad school in astronomy because I really enjoyed doing the research.
Mm-hmm. What kind of music?
Music, I was a jazz studies major, so I play guitar, and I was into a lot of experimental kind of jazz, modern jazz, I guess you'd call it.
Okay. And which of those did you think would be a harder career path?
Well, that's sort of funny. I mean, I actually was toying with the idea when I applied to grad school. I was thinking of it mainly as a day job, and then I'd be a musician, but I would go to grad school for astronomy because it seemed like a better employment option, which is sort of amusing thinking. I mean, music is probably worse than astronomy in terms of trying to get a job.
But it could well be, yeah.
But then I just ended up liking astronomy too intensely, so I really got into it after that.
Mm-hmm. So let's talk about stars in general. I mean, people looking at the subject from the outside will say, well, or they might imagine, well, that's a pretty mature part of the field. We've had this basic theory in place for 80 or 90 years or whatever, and but there's still some pretty major things we don't know, so talk about some of the things that we don't know about stars and stellar evolution.
The things that are understood pretty well is basically stable stars that are on the main sequence for most of their lives, stars like the sun, and so we understand their structure and how they go through their lives. The things that are not understood are the two ends of those, how they get there, so in other words, how stars form from the interstellar medium, and then how stars die and how they go from being a star to a red giant or a red supergiant, and then becoming a planet or nebula or a white dwarf, or in the case of more massive stars, how they reach their end as a supernova.
And people thinking about this in general might also think it's a clever trick because these are objects that take hundreds of millions or billions of years to live their lives, and we can't watch it happen. So how can we piece this story together anyway?
Yeah, this is a bit of a trick, and so what we do is we observe. Out in the galaxy, we see all these different types of stars, each of which is at a different phase of its life. And so then we try to compare that to what we expect from models of how stars evolve. And so we have a model will begin with how you calculate, starting when the star is born with a certain mass, how it'll go through its life burning its fuel, and how its core structure will change, and how the envelope of the star will respond to that. And then convolving that with a range of different amounts of stars at different initial masses. So there are a larger number of stars of low mass than and then there's a smaller number of high mass stars. And so you take those factors and put them in your model and try and match to what you see out, the number of different types of evolved stars that you see. And by doing that, you try to constrain the physics that goes into the model. The problem is that there are many very complicating factors. The models are all pretty simple, one-dimensional, perfect spherical symmetry stars that eventually, when they run out of their fuel in their core, they start burning the next fuel, and so you end up with a structure that has a series of shells. But in reality, there's a lot of convection that messes things up. There's also two key factors when you talk about massive stars. Are that on the one hand, massive stars lose mass, so they produce enough light that they blow material off their surfaces in winds, and the sun loses very little mass. It loses less than a billionth of its mass in its entire lifetime, but a massive star might lose half of its mass during its lifetime, and so the end product is very sensitive to what you assume in your model about how much mass is lost. That essentially the assumptions determine the outcome, and that makes the predictive power of the models not as good as you'd like, because they're very sensitive to what you think you already know. And one of the very complicating factors is that most stars are in binary systems, and in fact, as they go through their lives, if they have a certain initial separation, they're orbiting around each other, When one of the stars gets toward the end of its life and swells up and becomes a red supergiant, at that time the stars are then closer together because the star is getting bigger, and so they can begin to feel the gravity of the other star, and they can actually exchange mass, and they can exchange a large fraction of their mass.
Mm-hmm.
And it's almost like you're resetting the clock on some of these stars, because the other star will gain a whole bunch of mass and become basically a different star. And this used to be something that researchers in the field sort of brushed aside as a complicating factor, but now we're learning that that the fraction of stars that are binary stars, that are close binary stars that'll do this, is actually a very high fraction. Mm-hmm. And it might actually dominate what we see.
And is the endpoint of, and these are tight enough binaries that the endpoint of this is always a merger, or not necessarily?
Not always, but sometimes. The predictions are sort of that maybe a fourth or a third of the time the stars will actually merge.
Mm-hmm. Other
times they will donate mass to the companion, and so then the one that donates the mass will lose all of its outer envelope, and it'll produce one type of supernova, whereas the other star that has gained all this mass will then produce a very different type of supernova than what it would have done if it had evolved on its own. And so the research I do is I'm trying to make connections between the types of supernovae explosions that are observed and connect them to the types of stars and how those stars are ending their lives, and that turns out to be pretty complicated.
So let's go back to the beginning part as well, because, you know, again, in very simplistic terms, you know, how hard could it be? There's a nearly spherical cloud of gas, and it collapses and forms a nice star, and maybe there's some planets around it. But star formation is a pretty crazy, chaotic thing, right, mostly hidden from us, I guess. So how have we figured out any kind of reasonable idea of how stars form in general?
Yeah, I mean, what we try to do is you take a cloud, and you have a model of how the cloud collapses under its own gravity, and you know there's some angular momentum, so it should start to spin up and form an accretion disk. And basically how the disk feeds this protostar then determines the rate at which that occurs, determines how massive the star can grow in a certain amount of time, and it depends on the amount of mass that's available in the cloud. There are a couple of complicating factors, and one is, as you said, that stars form alongside many other stars, and they orbit around each other, and they smash into each other, and then you have sometimes massive stars, which when they're born, they start to have a very disruptive effect on their surroundings, and so then the radiation and the winds that come from a very massive star can actually clear away parts of the cloud and terminate the star formation process, and it can also affect the structure of the disks that are around some of the smaller stars that are nearby, and we actually see that. We see evidence of that when we look at places like the Orion Nebula. We see low mass stars that are very young that are still surrounded by these accretion disks, and they're being illuminated from the outside by these massive stars, and their disks that are trying to form planets are actually being evaporated. And so the types of observations we do, where we try to measure the mass of the disks that are still there, and we use other techniques to try and measure the rate at which the disks are evaporating to see if this will actually evaporate the disk before the star can finish forming and before it can form planets.
And what limit does nature put on the mass of a star? I mean, can you have any mass star?
There's actually a long history to that. So there are a couple of places where a limit could come from. One is that as a star gets more and more massive, it becomes more and more luminous. And so there's this idea of something called the Eddington limit, named after Arthur Eddington, where as a star produces more and more light, the problem is that photons carry momentum, and so the light that's produced by a star actually exerts a force pushing outward, which counteracts gravity pulling inward. And so if that radiation force pushing out is stronger than the force of gravity, the star should unbind itself. And so that would in principle be a limiting factor. It turns out that in terms of the structure of the star, that ends up not being a limiting factor, because as stars get more and more massive on the main sequence, the relationship between how the mass and luminosity relate to each other reaches a point that the stars they follow the same relationship as the Eddington limit, basically, so that a star, once you get up to stars that are 100 solar masses, if you double the mass, you'll double the luminosity. And so the math works out that you can always be at the Eddington limit, and you can still have more mass. You can add mass to the star, and you don't increase the luminosity enough to blow it apart. So there's really we don't think that there's a fundamental physical limit to the structure of a star. purely based on the Eddington limit. However, it may play a very important role in how the star forms. And so forming a star is a lot harder than just having a star that exists in equilibrium, because to form a star you have to take matter from a cloud and allow it to move inwards and accrete onto the star. And in that process, the process of accreting this material on the star also generates some luminosity, because the gas in the disk will heat up, and that will create its own radiation pressure as well as the light that's coming from the star. And so in the star formation process, there might be some limiting factor on upper massive stars based on the physics of how the accretion disk works, and that is something that is not fully understood yet. That's an active area of research. People are doing complicated three-dimensional hydrodynamic simulations of this process of a cloud collapsing to a disk and forming stars. And they're finding that some of the simpler ideas we used to have of assuming a simple spherical cloud, and you calculate the pressure of the radiation acting on dust grains, for example, in the cloud, would push the gas out, and it would halt the formation of a star of something like 30 solar masses.
Oh, okay.
Yeah, but we observe stars much more massive than that. And the answer is probably that as you accrete material in a disk instead of in a spherical cloud, you allow the material to be opaque. And so then if something's opaque, the radiation basically goes around the opaque blobs of gas, and that material can then make it onto the star.
And so if the nature of the limit in theory is a little unclear, what do observations say? What are the most massive, what's the most reliable high mass estimate for a star?
Well, there's a couple areas where it's a little tricky. So in terms of the star formation process, it's very hard to do, because massive stars form very quickly, and so they actually form the star while the cloud around them is still very opaque, and you can't actually see what's going on. So it's very difficult to observe the earliest stages of the formation of massive stars. However, when we look around us at star clusters, which is where most of the very massive stars live, because they're generally born alongside a much larger number of low-mass stars, so the most massive stars are always in clusters. When we look there, we do find stars that are extremely massive, and in some cases, when we're lucky, they're in a binary system, particular kinds of binary systems where if they're edge-on, we can see one star blocking the light from the other star. It's called an eclipsing binary system, and we can measure the mass very accurately in those cases. And then in other cases where we have a binary, where we can just measure the radial velocity of the wobble of the stars, the same way that people measure the radial velocity of stars and find planets. And we can use the observations of the radial velocity or of the eclipsing binary to measure the mass basically using Kepler's third law. We can weigh the mass of the star system, and we find the most massive stars that have been detected now are in the range of 200 to 300 solar masses. For many years, it was thought that there was a limit of about 150 solar masses on the maximum limit of stars. And the most massive ones that had been measured in binaries were around 80 or so. Right. But there have been some recent discoveries of even more massive stars.
And these are phenomena. I mean, these are amazingly, for astronomy timescales, short main sequence wise, right? A few million years or something.
They only live for a total of about 2.5 or 3 million years.
Right. Yeah. So barely longer than humans have been Homo sapiens. It's amazing. And that are when stars that massive live these short, violent, accelerated lives, are there actually synoptic? Can you actually observe variability or aspects of the formation process or early evolution in real time? Are there any things that can be done with sequential observations?
One of in the earliest phases when they're forming, we do see evidence of the formation process onto a massive star by looking at how the gas around them gets disturbed. So even though we can't see deep into the core of a cloud where the star is forming, we often will see outflows coming from the radiation pressure, and through the process of accretion, actually low mass stars and high mass stars will create outflows that eject some of the matter out. And so as that stuff expands into the surrounding medium, you can see it as it crashes in and shocks the surrounding material. And so we can use that as a way to try and identify massive stars that are still in the active phases of formation. And then we go, using mostly radio and infrared measurements that can see into the clouds, we try and measure the masses of the clouds and we try and estimate the gravity that's there and how massive the star is that's forming and how luminous it is. But we have never actually seen a very massive star that's in that. The star itself is mostly invisible to us. In terms of watching the evolution happen, once they form on the main sequence and become a star that's in a similar phase to the sun, where they're burning hydrogen in their core, that time scale is long enough that we don't observe changes readily. But then when their core runs out of hydrogen and they've got a helium core and they start burning helium, then they become supergiants. And some of them become red supergiants, and some of them, like Betelgeuse, and some of them become blue supergiants. And when this happens, they have the same mass, or even maybe less mass than they had before, but their luminosity goes up because the core is contracting and getting hotter. And when that happens, they get closer to this limit I mentioned before about the Eddington limit.
Mm-hmm.
And so then what happens is that the envelope of the star becomes very loosely bound by gravity, and so they're very easy to disturb. And what happens is that these stars end up they show visible signs on our lifetimes, or even shorter, a few years or months of sometimes very violent, rapid variability, where they'll eject a large amount of mass from the outer shell of the star, and they'll get brighter, and then they'll fade, sometimes on very short time scales. And so that is something we actually can watch happen. And that's a pretty exciting thing.
And is that, and presumably the theory and the simulations especially have moved on to be able to try and get down to explaining details of what's observed, or?
Well, no, not really.
No.
That makes it very hard, because the simulations, usually when you calculate the evolution and the lifetime of a star, what they do is they impose upon the model this idea that it's in balance, that it's in equilibrium. And the time steps in the calculations are actually pretty long. The shortest time scales are tens of thousands of years. And what happens with the observational evidence that we've been collecting in the last decade or so is that some of these changes that we're seeing are actually dynamical events. In other words, you have a shock wave moving through the star on a very short time scale that blasts the material off. And that actually changes the structure of the star. And from the point of view of the simulations, it's basically an instantaneous change. It's a change that happens faster than the time steps in their calculation. And so this is not something that was ever predicted.
Okay.
It's something that we're trying to come to terms with because it's an observed fact,
Right.
and trying to understand what the energy source is and how the structure of the star responds to this kind of thing. Because the insides of the stars are actually much more complicated, probably, than what the models assume.
Well, let's talk a little bit about the observational tools you use to diagnose these various phenomena, because a lot of especially on the star formation end of things, you're dark, dusty, opaque regions. So how do we even figure out what's going on?
So at normal visual wavelengths, what we mainly see is the hot gas that's illuminated by the ultraviolet radiation of young stars, and that's when you see things like the Orion Nebula or other star-forming regions. What you're seeing is the ultraviolet output from these stars once they're already born. To see them at earlier phases, we usually have to resort to infrared radiation or even radio emission, because the wavelengths are longer, and those wavelengths can penetrate through these dense clouds, these dense opaque, clouds that are opaque at visual wavelengths become transparent as you move to longer infrared and radio wavelengths. And so the trade-off is that spatial resolution or angular resolution, it usually gets worse. And so the picture basically gets more fuzzy as you move toward longer wavelengths. And so you pay a price of being able to see into the cloud by seeing it in less detail. And the way astronomers have gotten around that is by creating radio telescopes that work as interferometers, by using many telescopes together. And this is like the VLA in New Mexico, where you can actually achieve very high angular resolution even though you're working at the long wavelengths. And that has been an important tool to see deep into the clouds and actually see the details of the disks that are around these stars. And we're hoping now with this new radio array of telescopes called ALMA in South America, that's really going to revolutionize the field.
Right. So yeah, that's a good thing to talk about a little, ALMA, because it is one of our new frontier facilities. And this is not just continuum, there's a lot of line work being done too. So what is ALMA's capabilities? What kind of things you do that are exciting?
Yeah, so what you get at radio wavelengths that you don't get at optical and ultraviolet wavelengths is that you see a lot of emission from transitions of molecules. So things like carbon monoxide and all kinds of other molecules, ammonia, a lot of molecules that are existing in these cold, dense interstellar clouds, where the temperatures are low, and so
just tens of Kelvin.
Yeah, just a few tens of Kelvin. And so the transitions that are excited in these, basically what it does is the temperature in these clouds mean that there are collisions between atoms and molecules, and that makes the molecules vibrate or rotate. And when they do that, they emit light at a particular frequency. And so you can by detecting light at those various frequencies, you can figure out which molecules you're looking at, and you can use them as diagnostics to learn about the temperature and the density in that gas. And temperatures and densities are basically the things we want to measure, because that tells us about the pressure and the physics of what's going on inside of a dense cloud where the stars are forming.
And then with ALMA, of course, you get angular resolution too. How good is the resolution of ALMA?
So the spatial or angular resolution of ALMA is actually comparable to, or sometimes better than, the best resolution we can get with Hubble at visual wavelengths. So using a ground-based telescope in the optical, you're usually limited to around 1 arcsecond of angular resolution. And Hubble beat that by a factor of 10 by getting above the atmosphere. And so ALMA will do something very similar, a factor of 10 or 100 better than that, but looking at the radio. And it does this, again, by combining many telescopes instead of just using one dish of a radio telescope.
And for people who are familiar with VLA, what ALMA's doing is really at maybe 10 times shorter wavelengths typically.
Right.
And that brings you a whole set of key diagnostics that VLA can't do this kind of science.
That's right. You move into a regime that's sort of in between infrared and radio, where a lot of different molecules emit these signatures of their temperature and density. And these are very important diagnostics in the types of clouds that are forming stars. And so not only can we see extreme detail in some of the clouds that are forming stars in our galaxy, but it will allow us to do it'll provide a very sharp view of clouds that are forming stars in other galaxies at very large distances, a much better view than we've ever had before.
Right. So there you're not looking at the details, but as far as diagnosing how star formation works in galaxies across cosmic time, it's actually going to be able to say some interesting things.
Right.
And what is that? That's another interesting issue that, when we understand sort of the sun versus all other stars, when you have your nearby regions of star formation that you understand in gory detail, and sometimes too gory detail, it hopefully is informing us about what we see in other galaxies as we try and map out the history of star formation in the universe. Does it work that way? Can we tether that science?
Yeah, it's a bit of a leap, because the star formation regions that we normally study, like the Orion Nebula or other things that are nearby, are far less extreme in terms of the environment than what you get in galaxies that are at large distances, which are forming many more stars. And so one problem is trying to understand the difference between an isolated star forming region that you see in our galaxy and something in a faraway galaxy where you basically get the integrated light of the entire galaxy all at once as an unresolved blob, basically. And trying to understand how a range of different sizes of star forming regions all contribute to the star formation across an entire galaxy. But then there's another issue, which is that when we look far away, we're always biased towards seeing the brighter objects. And so there are classes of galaxies that we see at large distances that are much more common and much more extreme than any of the galaxies that are around us nearby. And these are galaxies where basically the entire galaxy is engulfed in star formation. They're basically like one gigantic region of star formation. And one of the differences is it's not just that you take something like the Orion Nebula and you scale it up, because what happens is by scaling up how widespread and how active the star formation is, you actually form a larger number of the very most massive stars. And they have very short lifetimes, and there you have a situation where those stars are putting out much more ultraviolet light into their surroundings and heating the gas much more than you get in an or star forming region in the Milky Way. And also they reach the ends of their lives, and there's so many of them that supernovae explosions are constantly going off and heating up the gas around them. And so the physical conditions in the gas in these galaxies are much more extreme than in the Milky Way. And so we don't know yet, but there are ideas that maybe this is actually going to form different types of stars. It may bias you toward...
Right. So that's an interesting cautionary note, because I don't always see that written into the papers of people who are looking at Eulers or whatever. They don't always put the caveat that, mapping that back to our understanding of star formation rate or any of the basic properties is not a reliable thing necessarily.
Yeah, astronomers do a lot of extrapolating where maybe the uncertainties in the extrapolation might not be valid because there are systematic effects that we maybe don't take into account, or we don't know that we're supposed to take into account.
What about the Orion, Taurus, some of the nearby well-studied star formation regions? Are there any what does star formation occur in rather gentler or sparser regimes, or does it require a large cloud that will eventually form hundreds or thousands of stars?
There is a whole scale, and actually what you mentioned, Taurus, is probably one of the lower end ones. It's formed sort of it's one cloud near us in the Milky Way. It's formed a smaller number of mostly lower mass stars. Orion is a little bit bigger, and it has formed one or two of the more massive stars. But even that is not close to the most massive stars that are seen. But there are regions in the Milky Way. There are a few dozen regions that are the most luminous and most massive star-forming regions in the Milky Way, and they come from molecular clouds that are about 1 million times the mass of the Sun, and they end up forming about a few percent or 10% of their mass goes into stars, and so they form these massive star clusters, which form the hottest and most massive stars that all live together in the same place. And you see those in spiral arms of the Milky Way, and you also see them in the galactic center.
Mm-hmm. Now, you've talked about molecules a bit and these cold regions where, molecules exist and we can diagnose them. I lose track of the number, but there's a pretty amazing number of different molecules that have been found in interstellar space, over 100 at this point.
I don't actually know the number, but yes, there are many, many molecules, some of which are what we would call organic molecules that exist in interstellar space. The most common ones are combinations of hydrogen, carbon, oxygen, and nitrogen, which is sort of what you expect. Those are C, N, and O, carbon, nitrogen, oxygen, are the things that are produced a lot from the ejecta of stars that are recycled back into the interstellar medium. And so when a massive star finishes its life as a supernova and explodes, a lot of the carbon and the oxygen and the nitrogen that has been burned, the hydrogen has burned into helium, and it produces carbon, nitrogen, oxygen. That material gets released back out into space when the star explodes. And when that material collects in a cloud, and it becomes a cold cloud, that it has when a molecular cloud has dust grains, it can shield itself from the surrounding ultraviolet radiation, and that allows the center of the cloud to become very cold and dense. And when the cloud is very cold and dense, then it can form these molecules. And so the most common molecules are combinations of those elements.
And what about, since it's of great interest for people worrying about habitability in exoplanets and other forms of us, how water is part of this picture too? It's a fairly abundant molecule, right?
Yeah, we see, for many years we've seen water, basically water vapor existing in star forming regions, because it gets excited by the molecules get heated up and excited by outflows from stars. There are shock waves that go through these clouds, and you see them mostly close to stars that are forming, because the water molecule needs to be heated up in order to be able to see it. But it is seen in a large abundance in interstellar clouds. It's out there.
And there's booze out there too, right?
Yeah, there's alcohol.
So you got everything except a huge olive needed for a martini.
Yeah, well, yes, that's true. There's also ammonia, a lot of ammonia out there, which is not as interesting to drink. But
and these, apart from the interest of having molecules like that, they're all very important for the story of star formation, right? They have important roles in how the clouds collapse and how energy is transmitted and so on.
And they serve as tracers of different conditions. So different molecules are more favorably excited at different temperatures. And so when we observe a cloud in many different types of molecules, we see the spatial distribution of the different molecules and can learn about the temperature structure of the cloud, and the densities where they form. And we sometimes see ices, so we see evidence of that these molecules sort of accumulate into more solid particles that, locally we see them in comets, for example. And so we see evidence of this emission in young stars that are forming as well.
Mm-hmm. And I haven't asked this explicitly, but because the exoplanet hunters are, doing the natural thing of looking around possibly isolated, but solar type stars, what are from what you know, planets are forming in these places like Orion and in these dense star forming regions, right?
Yeah.
There's no reason to believe that exoplanets don't form around all stars, regardless of environment.
That's right. I mean, we have not yet detected planets themselves in the disks in places like Orion. That'll be a very cool discovery when it's done. But we know that the temperatures and the size scales of these disks are comparable to what we think we need to form the solar system.
And it happened, the solar system, it happened pretty quickly. So when we look at disks in these star-forming regions, what evolutionary state are we looking at relative to when you might form planetesimals and then planets?
These may be in the phase where they're forming planets, and some people have even speculated that the presence inside a region like this might influence the formation of planets. So the formation process is generally very fast, so it's sort of 100,000 years or less. And it seems to be roughly what the age of the Orion Nebula is. Maybe that's a coincidence, but that's the age of some of the youngest stars in the Orion Nebula appear to be around that age. And so these disks can't be much older than that because they should be evaporating pretty quickly. Mm-hmm. And so whether or not there's any external influence on the temperature and density structure of the disk is an open question, I think. So for example, external radiation could, when it hits the disk, it could evaporate some of the gas, and some people have suggested that would allow the solid particles to more easily settle down to a midplane where they can then accumulate into protoplanets.
Right.
Yeah.
But these are not observationally tested ideas yet.
They're not. The types of things we observe are we see the emission from these protoplanetary disks, and by looking at the emission at various wavelengths, we can try to infer the sizes of the particles that are dominating the emission. And we do see emission from what we would call very large dust grains, so things that are larger than a micron, which are we think those are the seeds which will form pebbles and rocks and asteroids and planetesimals. There's an interesting side story to this for our own solar system, which is that when we look at compositions of meteorites in our solar system, we see inclusions of radioactive isotopes that are very special. So things like iron-60, which is a special isotope of iron, which has a very short half-life for decay. And iron-60, we think, is the only place it can be produced is in a supernova. And so the fact that we see that included in some of the meteorites that are found from our own solar system probably indicates that our own solar system formed very close to a supernova, or maybe multiple supernovae. So the sun probably was born in one of these regions where low-mass stars, like the sun, are forming alongside with very massive stars that are reaching the ends of their lives.
And is that implied as an actual causal connection, that the Wolf-Rayet gas cloud of our solar system was triggered into collapse by an actual event that we can see in the radioactive material?
Yeah, so that's something that's not proven, but there are models that suggest that you could trigger the initial formation of the solar system that way, so that you have basically a cloud of gas that's not collapsing under its own gravity, but it gets hit by the shock wave of the supernova, and that compresses it, and it and puts it just beyond its pressure balance and allows it to compress. It allows itself to be compressed by its own self-gravity. And so there are people who have suggested that may be what happened to form the solar system.
Well, let's finish talking about your favorite end states of stars or late phases of stellar evolution, because things get a little crazy there too. Yeah. What do you?
So my favorite thing, I guess, that is kind of a new result in the last 5 years or so, is that we've been finding evidence from from supernovae that there's a small fraction, maybe 8 or 9% of all of the supernovae we see. The supernova explosion occurs in such a way that the shock wave of the supernova smashes into material that's surrounding the star. And the trick is that that material has to be very close to the star, comparable to the size of our a few times larger than the size of our solar system. And we can, from various clues, using spectroscopy, we can measure the outflow speeds of this material, and we infer that not only is this stuff very close to the star, but it's actually very young. Or, in other words, the material surrounding the star was put there very recently. And the implication is that some of these massive stars actually go through eruptions or explosions before they finally explode as a supernova, just in the last couple of years or a decade before the supernova. So in other words, it's as if these supernovae are giving us an early warning sign that they're about to explode. And we don't really know why, but the fact that it occurs shortly before the supernova tells us that maybe this has something to do with the very last stages of nuclear burning. So as the star is burning hydrogen, during most of its life it burns hydrogen into helium, and then in the later phases it burns helium into carbon, and then heavier elements all the way up to iron. And the latest phases burning oxygen and burning neon take only a couple of years.
And silicon?
And silicon takes about a couple of days.
Okay.
And it only takes a few days to form an iron core. And so the implication is that in these very latest phases of a year or so, the star is becoming very unstable because it's generating too much energy somehow, and it blows itself apart.
So and that's interesting. Well, just also let's put a number on it, because it's I'm sure it's an interesting number for a 10 solar mass star. I mean, how much iron has been made by the end of its life?
About a solar mass.
Yeah. That's amazing.
Sometimes less than that, but.
So these symptoms of incipient explosion which of those phases do you think they're associated with?
Well, we think they're associated with the very latest phases, but because they're rare, we also think it's probably limited to the most massive stars as well. Mm-hmm. That only stars above maybe 30 or 40 times the mass of the sun will actually do this. And when they do this, they're very powerful precursor explosions. They may eject 5 or 10 times the mass of the sun that's lifted off the star and put in its surroundings, which is then hit by the supernova. So these stars these pre-supernova eruptive phases actually modify the structure and the composition of the star just in a few years. And so from the point of view of being an observational astronomer who goes out and looks at these things, that's a very exciting thing to do, because we've had now a couple of cases where we've actually seen the eruptions and then seen the supernova.
Wow.
And that happened last year.
Are these always type 2s? What?
Well, no, there's one that wasn't a type 2. But they're always a particular type of supernova that has narrow emission lines in their spectra, and the lines are narrow because the material is slow. Mm-hmm. So there's most supernovae, when a red supergiant explodes, the outer parts of the star are ejected at very high speeds. And so when you look at a spectrum of the star, the emission lines from particular elements will be smeared out because the material is moving so fast. But for these objects, what happens is the star lifts a few solar masses of material off the surface of the star, and it kind of levitates it above the star. It ejects it with just enough energy to remove it from the star, and the stuff is moving very slowly, 10 or 100 times more slowly than a normal supernova. Mm-hmm. And so then when the real supernova finally occurs, that although that stuff is moving fast, it crashes into this slow stuff and gets slowed down. And so the spectrum that you see of this kind of supernova doesn't have these broad smeared outlines, it has narrow lines. And so it's usually hydrogen, but there is one case where it was narrow helium lines. So somehow the star had already gotten rid of all of its hydrogen, and then did this and blew off the outer parts of the helium core. But it's mostly it's hydrogen. So we think these are evolved massive stars that have lost a lot of mass, but not all of their hydrogen mass. This was actually a very important result in the sense that it totally contradicted most of the models for stellar evolution. So the standard models for massive stars are that they have these strong winds which remove all of the hydrogen, and the star will explode with just a helium or carbon core. But the fact that we're seeing these very massive stars exploding and they still had their hydrogen was actually quite a puzzle, and that's still not solved.
Wow.
Or it hasn't been reconciled with the models, but we know that the models have some assumptions in them that are probably oversimplified.
Mm-hmm. So I have to mention, that's a great grant opportunity. I mean, if NASA is trying to save us from asteroids, you should set up an early warning system for the supernova that goes off close enough that it might kill us. And,
Right.
And there's got to be an opportunity there.
That's a hard sell, though, because the probability of that is very small.
Well, you can.
Yeah.
Yeah, people don't understand probability, so I'm sure.
Well, unfortunately, though, the people on the NASA panels probably do understand.
That's true. Yeah. But
Yeah.
it's amazing to have a warning for that, because I mean we are overdue for a supernova in the Milky Way, and everyone's gonna train every facility they can onto it. It'll be a wonderful time.
We are well overdue, and there are a number of massive stars close to the sun that are good candidates for the next supernova. But
How close?
so hundreds of light years.
Mm-hmm.
So
it's a ringside seat.
yeah,
definitely.
basically. I mean, these are the nearest ones. If they were to explode, they'd be visible during the day.
Mm-hmm.
They'd be very bright for the most part.
Actually, too bright for a lot of big telescopes.
Well, this
to
is an
observe.
issue. A lot of our telescopes are almost too big to observe these things. If they were to go off, we would need to use either small, like amateur type telescopes, and there are networks actually of amateur astronomers who are actually now getting spectra of very bright stars and monitoring their variability. Because you can, off the shelf, you can buy spectrographs and put them on the back of a celestron telescope or something, and take time sequences of spectra as stars vary.
Yeah.
And I should say this too, in terms of looking for supernovae, most of the nearby supernovae, and now by nearby I mean in nearby galaxies, so out to a few million light years away, most of those are actually discovered by amateurs who are out looking for supernovae every night.
Right. And that's it's an important part of our business, really,
Right.
like the interface between high-end amateurs and the professionals.
It's a lot of what I do. So I get electronic notifications when there's a new supernova discovered, either by a professional supernova search like the Palomar Transient Factory or some other ones, or by amateur astronomers who discover supernovae, and then I go and try to get spectra of these things.
Right. Okay. Well, thanks, Nathan. That's
All right.
been fun.
Great. Thank you.